Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over rate law practice problems. So this is a continuation of an introduction to kinetics. So let's get into this. So here's practice problem number 1. So here in this practice problem and the other practice problems I'm going to show you is how to find the rate law for a particular reaction when you're only given a data table. So we're going to follow those steps I talked about in my last video and show you how you can go through the steps to get the right rate law for the reaction based on the data that you are presented with in the table. So let's get into this. So here we have our table of information. Here's our balanced equation. So let's figure out what the rate law is. First thing you need to write is your skeletal reaction equation. So we'll write that over here. So the rate is going to be equal to rate constant multiplied by the reaction, the concentration of one reactant, so F2. So F2 raised to the power of X multiplied by another reactant. So the concentration of this reactant, ClO2, raised to its exponent. I think I said coefficient, I meant exponent, x exponent, and we have y exponent there. And so here we have our skeletal rate law expression or equation. And so now what we need to do is we need to figure out what x and y are and see if either of these stay in the actual expression. So this is where your data is going to come in. So you've got data here, and what you want to do is find two trials where one reactant is constant and the other reactant is changing, and we want to compare how the concentration of one reactant changes and how that affects a change in the initial rate of the reaction. Okay, so here we can start with these two, right? So I see that this one here is the same. So trial one, I forgot to put trials here. So let's put trial. So this will be the trial number, and this will be 1, 2, and 3. So we'll look at 1 and 3. So you'll see that ClO2 concentration is constant between these two trials. And here we see that the F2 concentration is not. So what we want to do is look at how they change and look at how the rate changes here. So what we can do is look at the initial rate of change. And so we see we got 1.2 times 10 to the negative 3, and here we have 2.4 times 10 to the negative 3. So it doubles. So what you want to do is for the rate, you want to put a 2 because it doubled. So let's put a 2. So we'll put a 2 here. And then we'll look at, where is it? The fluorine concentration, F2 concentration between here and here, and you'll see that that doubles as well. And so we'll put a 2 in for that concentration. So we'll have K here, and we'll put a 2 in for F2. Let's just put a 2. So the concentration doubles, and we'll have our X there and then we'll have the ClO2 to the Y. Now, if anything is constant or stays the same, we need to get rid of that from our equation. So K is constant and ClO2 is constant, so we're going to get rid of those. So those go bye-bye. So then what we're left with is, so, oops. Okay, lights went out again in Georgia. Okay, so I'm not in Georgia. Uh, so this goes away too. And what I'm left with is 2 equals 2 to the x. So then I asked myself, okay, well, what does x have to be in order for 2 to the x to be equal to? Well, that means that x has to be 1. X 2 to the 1 is going to be equal to. So that means x is equal to 1. And that's how you do it. So we know what x is now. So this is first order with respect to the change in concentration of F2. Okay, so there's another way we could do this, maybe a little bit longer way. So let me show you that way. Now, what you could do then, use this equation and write it twice for each trial. And then divide the two, and then whatever stays or whatever is constant gets we get rid of, and whatever is left over we work with. So we could look at trial number 1. So that's goes from a rate of 1.2 times 10 to the negative 3, and here's our concentrations. So we can write that down. So that would be 1.2 times 10 to the negative 3 is equal to K times the F2 concentration, which is, oops, 0.10 x times our concentration here, which is 0.010 y. So that's the first trial. And then you set up the second trial, same thing. So now we have 2.4 times 10 to the negative 3 is equal to K again. And our concentration of F here is 0.2. So 0.20 x times, again, 0.010 y. So then now all you have to do, now that you have these two expressions, we divide one by the other. And so if I take this one and put it down here, so I have 1.2 times 10 to the negative 3 is equal to K times 0.10 x times 0.010 y, and I divide them. So I'm looking at these two here. So if I divide them, well, this divided by this is 2. K's cancel out. This to the x over this to the x ends up being 2 to the x. And then these cancel out because they're the same. And so I get the same expression all over again. So this is a little bit of a longer way, but it works too. You can just fill in the data to the rate law and then cancel out anything that's the same, and then calculate whatever number you get when you divide. So you divide this by this, you get 2. You divide this by this to the x, you get 2 to the x, right? And so then you get x must be 1 again. So that's just maybe a little bit longer way to do it, but it works as well. Okay, so let's go ahead and do the same thing for our ClO2. So we now know that x is equal to 2. Now let's look at 2 other concentrations. So now this time we want to keep F2 concentration the same and look at how ClO2 changes. So these two, we see that F2 is the same concentration. And here we could see that the ClO2 concentration quadruples from here to here. So, and then let's look at this. So let's look at this again. So with the rate, if we look at the rate, 1.2 times 10 to the negative 3 becomes 4.8 times 10 to the negative 3, and going from trial 1 to trial 2. So this quadruples, so we're going to do a 4. So rate is 4 equals K. Now, we have our F2 concentration the same, so we'll just put F2, right? And this is now a 2. Or we'll just leave that at x as x for now. And then we look at our ClO2 concentration. How does that change? 0.010 to 0.040. So that also quadruples. So we'll put a 4 in for the ClO2. So we'll put a 4, and that's going to be to the y. And then anything that's constant, we get rid of. So K and F2 are constant in this situation. So this is constant. So we're going to get rid of those. So K is gone, F2 is gone. So now we're left with 4 is equal to 4 to the y power. And again, what does y have to be in order for 4 to be equal to 4 to the y to be equal to 4? Well, again, y needs to be 1. So 4 to the 1 gives us 4. So y is now 1. So y is 1. Oops, did I say 2? That should be 1. Sorry about that. So x is 1, y is 1. So now we've figured out our coefficient, our exponents. So our final rate law is going to be the rate is equal to K times the concentration of F2 raised to the 1 power times the concentration of ClO2 raised to the 1 power. We normally don't write ones, so we can erase these and just leave that expression. So there's our rate law expression there. So let's go on to problem number 2. Okay, so here we go with practice problem number 2. In this practice problem, I'll go a little bit quicker since we've gone over the steps slowly before, so we can do this a little bit more quickly. Okay, so practice problem number 2. Here we're not given a reaction, we're not given an equation, but we don't need one to figure out whether what the rate law is going to be. So the first thing we want to do is write our skeletal reaction expression or rate expression. So it's going to be rate is equal to K times, and in this case we're dealing with A and B. So we have A raised to the power of X times concentration of B raised to the concentration or the exponent of Y's raised to the Y power. So now we need to figure out what X and Y are. So let's look at A. Let's do A first. So here we want to keep B constant. So if we have these two, trial 2 and 3, we see the concentration is constant for B, but we notice that the concentration doubles for A. And so here, this is going to double. So A, we'll put a 2 in for A, but look at the rate here. The rate stays the same. So it stays the same, so it is 0, or it's going to be 1, right? So here, if we were to divide these two, it would be 1. So it doesn't increase. So this is going to be, we'll replace the rate with a 1 since it stays the same, equal to K, and we said A A doubles. So we're going to say that's a 2 because it doubles, and multiplied by b raised to the y power. But k and b are constant, so we get rid of those, and we get 1 equal to 2. Oops, I forgot my power here. Don't forget the power. That's really important. So this is 2 to the x power, since we're replacing this with 2. And so we have x there. So then the question is, what does x have to be in order for 2 to the x power to be equal to 1? And that is going to be your 0. So x has to be 0. So again, in order for this to be 1, in order for 2 raised to the x power to be 1, x is 0. So x has to be equal to 0. So that's 0 power. So if x is equal to 0 here, then this means that this whole thing is 1, and so it's not part of the rate. So that's going to be 0. So we're not gonna have that in our final reaction rate expression. All right, now let's look at B. So we want to look at B, see how B changes. We're going to keep A constant. So A is constant between trial 1 and 2. So we'll look at trial 1 and 2. So notice that the initial rate of B goes from 1 to 2 molar. So that doubles. So we're going to replace B with 2. So let's erase this. So we know x is equal to 0. And so now we'll replace the rate. So between these two, B is doubling, but you'll see that the initial rate doubles as well. So both of these will replace with 2 because they double, right? So then the rate is doubled. So that's a 2. That's going to be equal to K times A to the x multiplied by, b to the y, but b is going to be 2 because it doubled. So that's going to be 2y. And once again, k is constant, a is constant. We'll get rid of those. And so we get 2 is equal to 2 to the y. And again, in order for 2 to the y to be equal to 2, y has to be 1. So y is going to be equal to 1. So now we have our x and y. X is 0, y is 1. So we plug that into our rate law. So x is equal to 0, y is equal to 1. So the rate is going to be equal to k times the concentration of A raised to the 0 power multiplied by the concentration of B raised to the 1 power. Since anything raised to the power of 0 is 1, this is going to be removed. So the final rate law expression is going to be the rate is equal to K times the concentration of B. And so here you can see that the overall rate order of the reaction is going to be 1, which is the same as the order of the reaction with respect to the change in concentration of B. Okay. Last time for problem number 1, we had 1s for both of these. We had a 1 and a 1. So the individual order of the reaction with respect to A was 1, with respect to B is 1, but the overall order of the reaction was the 2 added together. That would be an overall order of 2. Okay, so that's problem number 2. Let's move on to problem number 3. Okay, here we go with problem number 3. So let me change this to a 3. And again, we're not given any chemical reaction, but again, we're just given the data table, and that's all we need. So let's first write down our skeletal reaction rate expression. So the rate expression is, again, rate is equal to K. And here we have NO concentration and Cl2 concentration. And just to point out that the zero here, the O or zero at the end here means not or the initial. So this would be the initial concentration of NO, the initial concentration of Cl2. So that's what that zero at the bottom indicates. Or so here we have our K, and so we have the concentration of NO to the X power multiplied by Cl2 concentration to the Y power. So let's do NO first. So we want to look at NO change in concentration. So we want Cl2 to stay the same. So we want to look at these two here. So trial 2 and 3, Cl2 concentration stay the same. But notice what happens to NO2 concentration. The NO2 concentration is doubled. What happens to the initial rate when you double the NO2 concentration? Notice here that we have 2.86 times 10 to the negative 6. Here we have 1.14 times 10 to the negative 5 here. So this is a bigger number. If you were to take this number here and divide it into the bigger number, take this number, divide it by this one, you would get a 4 here. Or so this would be quadrupled. So when you double the initial concentration of NO, you quadruple the initial rate. So that means we're going to put a 2 in for the NO. We're going to put a 4 in for the rate. So the rate is 4. That's going to be equal to K. 2 for NO, so that's going to be a 2 raised to the X power multiplied by Cl2 to the Y power. Again, since K and Cl2 are constant, we get rid of those from our equation, and we get 4 is equal to 2 to the X power. So 2 to what power gives us 4? Well, that's going to be 2. 2 raised to the 2 power is 4. So that means X is equal to 2. Now let's go ahead and do the same thing for chlorine. So we want NO to stay the same, NO concentration to stay the same, and we want to look at the change in chlorine. So here for trials 1 and 2, the NO2, the initial NO2 concentration stay the same, but notice that chlorine doubles. What happens to the initial rate when chlorine doubles? It also doubles. So we're going to put a 2 in for both of those. So if we take our equation and rewrite it, so for chlorine, it's going to be the rate is equal to K, and then we got NO. Since NO is constant in this one, NO to the X. And so the rate we said is 2. And chlorine also doubles, so that's going to be 2, and that's going to be to the Y power. And again, in this case, since K is constant, in this case, NO concentration is constant. So we get 2 is equal to 2 to the Y power. So again, what 2 to what power gives us 2? Well, that's going to be the power of 1. So 2 to the 1 power is 2, so Y is 1. So Y is equal to 1. We now have our exponents. So that means that the rate law is going to be rate is equal to K. times NO to the X, which is 2. So NO concentration to the second power times Cl2. Y is 1, so it's going to be Cl2 concentration raised to the 1 power. We don't write the ones. So this is our rate law for this reaction. So the rate law, or the rate, is second order with respect to the concentration of NO. It's first order with respect to the concentration of Cl2. And overall, it is to the third order, since 2 plus 1 gives us 3. That would be third order. So overall, the order of this reaction is third order. Okay, so let's go on to our last problem, problem number 4. Okay, so here's problem number 4, our last problem. I'm going to go over this one pretty quickly. So again, we have our reactants, their concentrations. We don't have reaction, but this time we're going to determine the rate law and calculate K. So let's do our rate law. So we have rate is equal to K times the concentration of S2O8, 2 minus, to the X times I minus to the Y. So let's hold I constant. So these two are constant. So let's look at how this doubles, or how this changes. So you go to 0.08 to 0.16, that doubles. And going from this rate to this rate, that doubles as well. So they're both 2. So if we put in a 2 for the rate, and we put in a 2 for this S2O8 2 minus, raised to the X power, dropping everything else, we get 2 equals 2 to the X. That means X is 1. Do the same thing now for I. We want to hold this constant, so these two are going to be constant. And if we go from this one to this one, it doubles. And if we go from here to here, it doubles. So same thing. So the rate, we're going to put in a 2 for the rate, 2 for the I, to the Y. Everything else drops out because it's constant. And again, we get 2 equals 2 to the Y. So Y is 1. So they're first order with respect to their concentration. So the rate is going to be equal to K times S2O8, 2 minus concentration, multiplied by I minus concentration. So there's our rate law. So now let's find K. How do you find K? Well, we want to solve for K. So K is going to be equal to what? That should be rate, not rad. So it's going to be the rate divided by the concentration of S2O8 2 minus, multiplied by the concentration of I minus. And then all we need to do to find K is take any of the values in any of these 3 trials, plug them in, and we get K. And it doesn't matter which trial you use. So we could take the first one, right? So then the first one, the rate is 2.2 times 10 to the negative 4. And we need to put in our units because we need to make sure that our K has the right units. So it's going to be M over S, molarity per second. And then we have this, so that's going to be 0.08, 0.08, and that's a molar for molarity. And then we put in 0.034 molar for I, and we just calculate. And we got to cancel out our units. So here we're going to have, what did I get? The answer is going to be 0.081 over molar seconds. And that is our K constant. I hope this is helpful. If you enjoyed this video, then please like, share, subscribe to my channel. Put a comment down below in the comment section. Let me know how you think or what you think. Thanks for joining me.